Exciting. Okay, welcome to Big Data Brews, but today we're drinking tea and water with Vijay from Microsoft.
Hello.
Would you please introduce yourself and share a little bit of your fascinating background with us?
Sure. Thanks, Stefan. Thanks for inviting me. I'm Vijay Narayanan. I head the data science and the machine learning algorithms team in our data group in Microsoft. So about myself, so I've been with Microsoft, I joined Microsoft about 3 years ago, three and a half years ago. And it's been a real great experience trying to work on defining the next generation data and analytics platform. So we have this vision that Satya, I think, laid it out beautifully when he became the CEO about 2 years ago now, that he really feels that his vision for the world in the next decade is that something that will be driven by data and by intelligence, by intelligent apps driven by machine learning.
Yeah.
And that's, I think, probably captures a lot of our investments and our focus in building out what we feel is the next generation platform for data and advanced analytics. So before Microsoft, again, it was a fantastic experience. I worked at Yahoo Labs in Yahoo for about close to 7 years, which again was just an incredible time because there was a time when Yahoo was really building out the whole Hadoop platform, the early generations of Hadoop. And I had a fantastic opportunity to work with some of the pioneers of the Hadoop ecosystem at that point in time. I was working on primarily machine learning and building machine learning applications in for various problems like content recommendations, problems in advertising, computational advertising. How do you understand users, user behavior modeling, personalizations, recommendations, etc. And earlier, before that, I worked in a company called Fair Isaac for about 3.5 years. Which again, Fair Isaac is I would say one of the pioneers of building analytical products, data and advanced analytics products. So if you have ever used the FICO score, it's a Fair Isaac score that's been around for more than 40 years now as the gold standard for credit risk. And there, I really cut my teeth and learned how to build products leveraging data, leveraging machine learning to solve real problems. So very good opportunity where we started out as an R&D group trying to, at that time there was a lot of fraud around identity theft and application fraud. Because as you might imagine, a lot of commerce was moving online. But unfortunately, the systems were not really very robust enough. There was a lot of fraud going on. It was fairly easy to steal someone's identity at that point in time and do a lot of identity theft. So it is really becoming a headache. So we worked on the problem from R&D, built a prototype of a solutions, worked with customers, and then realized, hey, there is really something we can use data and analytics to solve this problem, and built a product out of it, which is still in the market now.
But you have a completely different background, though.
Yeah.
Do you mind to share that?
Sure. So I was trained as a professional astronomer before I moved to the industry about 15 years ago, and I did my PhD in astrophysics, working on trying to build computational models to understand the growth of structure in the universe. So I'm sure most of you might know that the universe is now about 13.6 to 13.7 billion years old. But there's always this inherent question, okay, what was it at the beginning of the universe? And most of the popular hypotheses say that it started with Big Bang, and it was this one small soup of matter and energy, which was also very smooth. But if you look at around us, the universe is very clumpy, right? Right now, we see obviously planets at very, very small scales, stars, galaxies, and clusters and superclusters of galaxies. But there is very nice pattern to them. They're not homogeneous. There's a lot of rich structure in the universe at various length scales. So there's always this question about how did such structure arise from something that was as smooth earlier? And most of the popular hypothesis was On that smooth hypothesis, on that smooth background, there were these very, 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 very tiny ripples, tiny fluctuations in density, right? So what really happens is, and then from that point onwards, gravity takes over.
Okay.
Right? So you have certain regions that are slightly overdense. And when I say slightly overdense or underdense, these are really about 1 part in 100,000.
Okay.
Right? So they're really that smooth. And you just have about 1 part in 100,000 small fluctuations in density.
Okay.
So now imagine a place that's higher dense in like a region. So that starts attracting more matter towards it. So then it becomes more dense, right? And then it starts attracting even more matter around it, right? So then it becomes clumpy very quickly. Now all of these things, it turns out that if the universe was static, there was no hope of being able to reverse this process.
Yeah.
But there is this beautiful phenomena happening, which is that the universe as a whole is expanding.
Yeah.
So now we have two counteracting forces, right? There is gravity, which is trying to like clump things together. The universe that's like expanding and pulling things apart. I mean, imagine you have a sheet where some parts of the sheet are trying to collapse and become knots, but the sheet as a whole is expanding. So you have like two opposing forces. It turns out that you can, from current observed data, try to reverse this process to some extent. So you can technically run gravity backwards and still have
in a simulation.
In a simulations.
Okay.
Right? Of course, in a simulation. Try to undo some of the effects of gravity and try to really understand how the universe looked like 13 billion years ago.
And you worked on that in Princeton.
Yeah, so I did my PhD in Ohio State. Which is where I worked a lot on building the computational models, the theory behind it, but also worked on it very closely with data. So I was what I really would call as an observational theorist, where we would go collect the data, bring it in, use them to test theories. Now, the challenge with the universe is there is only one universe, so you only get to see one realization of this phenomenon. And you have to test multiple models against this one observed data point. So, and the thing is, you cannot run the simulation again. I mean, you cannot run this process again. So there is no way you can create other samples of the universe. You got what you got, and you have to work with it. Wow. And then I went to Princeton, where as a postdoc after I finished my PhDs, where I really became interested in saying, okay, how do we take data at large scale and compare against these theories? It was a really fantastic time at Princeton at that point in time, because Princeton was really driving a big initiative called the Sloan Digital Sky Survey, which was one of the most ambitious astronomical projects done. One of the very first, what I really call as the modern large-scale surveys of the universe. So we were taking images of about 1/4 of the sky. And some of you know the universe has about 4 pi steradians, and 1/4 of it is pi. So we call it the Pie in the Sky project. Really imaging the sky in about 5 different wavelength bands, and trying to observe the structure, understand how the galaxies, the clusters of galaxies, the superclusters are all looking like within our neighborhood, and comparing that with these models. In the process of doing that, what we did is we had an observatory, we had a telescope, a dedicated telescope for this in New Mexico. That would run every night, and we were just at the point of commissioning the survey and trying to collect this data, trying to process the data. Now, if you're familiar with how data is collected in astronomy, effectively there are telescopes which collect the photons, collect the pieces of light coming from distant galaxies, and focus them onto a plane where you keep these CCD detectors, right? So these photons go and excite some electrons there. These electrons flow. There are CCD devices. You collect the charges, and you know where are the bright points of light at any point in time. In doing that, we were collecting about 1 terabyte of data on a good night. Now, terabyte of data is probably nothing now, but imagine this is in early 2000s. Before we had the terms big data or cloud or anything. So we had a really interesting problem on our hands, which is a good nights of observing will give us 1 terabyte of data, and we needed to process them because these were raw devices, and there were all sorts of junk in these images, right? There would be airplanes flying that would be imaged. There would be meteors. Some of them would go out of focus that you will need to correct. There is moon. There was just a whole boatload of junk that'll be there.
Dirty data.
Oh yeah, lots of dirty data, right? Lots and lots and lots and lots of raw dirty data, right? So it really became the question of, and since there was lots of them, there's no way you could do them manually. Because till then, people would go get the surveys, they would sit in front of computers, write software and analyze them. But this one, we were just getting so much data that you have to build these automated processing pipelines and process them on one night, just to keep up with the pace of data collection. So someone would physically pull out a hard disk in New Mexico, ship it to Fermi Lab in Chicago, and we had these big collections of machines. Remember, this was before Hadoop or before any of the cluster computing technologies, right? So really, we would have these like 100 machines where we would load the data, try running them, and 5 of them will fail. For various reasons. The machines will fail, the disks will fail, the software will fail because it hit something very unusual it hadn't seen before. Because remember, we are really processing data that nobody has seen before, and we want to do them in an automated manner, and things will fail. So really, we were sitting around trying to do a lot of work, trying to understand how do we build these large-scale data pipelines. How do we process all this data very efficiently? How do you write intelligent algorithms for doing this? I think that was one of the first what I would really call as big data projects, at least the ones that I had the opportunity to be part of, and really stoked my interest in data processing, analytics, automated data mining, machine learning, etc.
Did you use machine learning algorithms then to process that data?
Yeah, at that time we didn't call them machine learning algorithms, we just called them statistical algorithms.
Yeah.
Absolutely, right? So
what do you use?
So we wrote a lot of them because there were no off-the-shelf techniques for that. So let's take a simple example, right? Say a very simple case. Suppose just there's a star, and the photons are coming from it. The star is so far away that for all that you know, it's a point, right? It's just a point source of light. Now, if there is no atmosphere, if there is no air, if there is no turbulence in the air, etc., the photon coming in will just come and straight away fall on one point in a detector. Yeah. And you can just count how many photons were there, and you know how bright the star was, how bright the star is. But unfortunately, what happens is we have the atmosphere, and which has lots of this turbulence. So around this, there are temperature gradients, there are lots of eddies of currents going in. So the photon is really doing this. It is like really dancing around. The first photon might dance around like this and fall a little bit here. The second photon might dance around and fall a little bit there. So really what starts out as a point source now ends up as a smudge on your CCD detector. So now what do? You have to now correct for it. Because a single source of point is now being convolved. If you're familiar with the Fourier transformations, effectively think about it as a transfer function. The atmosphere has a transfer function that takes a point source and spreads it out into a it's really called a point spread function because the point is now spread into the So really you'll have to measure the point spread functions, and this point spread function varies over time, varies over space where you are collecting. So you have to now model the point spread function and measure how many total photons, and if you have two stars that are close to each other, they're going to get smudged.
Of course.
But they'll get smudged in a way like this.
Right.
So can you separate them out? Can you at a given point, can you measure how much of the light came from this star and how much of it came from the neighboring star? So you build models to fit these models. Right? So you're effectively doing large-scale model fitting over these like literally hundreds of millions of images and sources of points of light, etc. And doing them across 5 different bands. So a lot of work there. And then what our real goal, though, was to use this survey to understand the structure of the universe, right? Because that was the original problem we started out with. We ended up having to solve a lot of these data problems in the middle. And our real goals were to say, hey, can we detect objects that are very far away? Right? It turns out that there are objects called quasars, which are very, very, very small sources of light. So they are called, basically quasar stands for quasi-stellar radio sources. They're very, very small. They are point sources of light, but they're so bright. They're as bright or much brighter than even typical galaxies. So the question is, what really powers them? And since they're so bright, they can be seen very far away. Now we have a much better understanding of these things. We think they are powered by black holes, matter falling into black holes, and light getting radiated from them. But really, these are very, very small, but very, very bright sources of light that are very far away. So think about them as like beacons that are so far away. So Turns out that if you find these quasars, they're incredibly hard to find because first of all, since they are so far away, they're faint. And they're also so far away and they're so rare as well. So you can go like hundreds of thousands of objects and not find a single quasar. So there's no way that you can go hunting at them one at a time. You have to have automated techniques that go and hunt them. And they're also very interesting for various reasons because light coming from them really has traveled to us through the various matter in the universe, right? Between us and the quasar, there's so much of matter that's
I assume you can measure this then as well.
Correct. So you think about them as a big skewer.
Right.
They're like a big skewer of light coming from there to there.
Right.
So if you study the properties of that light, if you study the spectrum, you know something about the physical characteristics of the medium between us and the quasar, the chemical properties, the thermodynamic properties, all those things. So it's fantastic skewer through the universe, if you would call them. So there's a lot of interest in going and finding these things. The challenge, of course, was how do you find these things that are very far away, that are very faint, because the fainter they are, the farther they are, which means that you're also studying what happens even earlier in time. So there's a lot of value in detecting, like discovering these things. So we, at that point in time, used this data to discover some of the farthest quasars that had been discovered at that point in time. And we discovered a bunch of very interesting astrophysical phenomena that was happening in those periods. So there's a lot of scientific payoffs from that. But personally, just an incredible opportunity to think about all these large data problems. How do you handle them? All the way from how do you store them? How do you process them? How do you account for machine failures? How do you fit these models in an automated manner to infer the signals? A lot of how do you pull out signals from very low signal to noise, lots and lots of raw, dirty data. So very exciting work at that point in time, which really got me very interested in this whole notion of data and machine learning and automated processing, signal extraction, etc.
Did you had a situation in your professional career where you had this realization, oh, wow, yeah, that's exactly the same thing I did, at my time at Princeton and before, and I used it to detect quasars, but now it's exactly the same algorithm. Did you have a situation where you're like, oh, yeah, actually, this is exactly the same as this?
Yeah, so a lot of, I think, modeling, as we call them now, right? I mean, machine learning modeling or data science or model fitting really comes down to assuming a characteristic shape for a function, for an underlying function, relating objects. I mean, relating either an input to an output or the structure of a sentence or something, and trying to fit the parameters there. Now, if you remember what I said was, hey, stars come in as point sources and end up as smudged and have a certain structure to it. And this structure could be something fantastic. For example, if you're really lucky, they could be very nicely Gaussian. And all that you have to do is just measure the width of the Gaussian. Which, if you have a single point light here, and they both become Gaussians, then it's fairly easy to deconvolve them, right? You just need to estimate two parameters and you're done. But they don't, right? Very often what happens is, because this smudging is caused by turbulence, it depends on what are the characteristics of the eddies in the atmosphere. And sometimes you might have lots of small eddies and then there are a few big eddies. So this is very rarely very nice Gaussian. There are tails around them, so they're probably fatter, or sometimes they're skewed like this. There's lots of very interesting model fitting exercises that you do. And the beauty is you don't know how these models are. They're changing by time, they're changing by location. So inferring these models, and so in effect, right now, most of the models, for example, assume some sort of relationship, either it's a Gaussian relationship or some sort of parameter function that's a Poisson or it's binomial or something. Here, there's no such well-defined function. So you have to really estimate the shape of this function and then use this function to then fit a bunch of data. So this notion about using these basis functions and fitting to different models, in hindsight, looks like, now that I have a better understanding of some of the foundations of machine learning, looks like there's a lot of such problems which are fundamentally very similar, model fitting. Right. At least when you take regressions, you take any type of discriminative models, maximum entropy models, or any of these things. at the end of the day, they come down to assuming some functional form of the relationship between multiple parameters and fitting for the parameters of these models.
Yeah.
So it's a good realization to me, but also realize that, hey, that's what a lot of statisticians have been doing for 300 years.
Yeah.
So it's also pretty humbling to know that, I mean, Gauss could have done probably most of what.
We might have a little bit more compute power, though. Yeah.
Oh, absolutely, right?
Yeah.
So I think fundamentally, the big explosion that's, I think, happened in the last 10 years is absolutely, as you said, the growth of computational power.
Yeah.
Just become incredible, right? I mean, you hear and you learn these, you read these articles that say, hey, an average smartphone today has more computing power than the computer that landed humans on the moon.
Yeah.
But then, when you think about it, it's outstanding what they were able to do 50 years ago, 49 years ago with that computing. So really, I think it now falls upon us to take advantage of this incredible computing capacity now, and what we should be doing. And also given that the amount of data that's now being collected, that's now being stored, that we have the opportunity to work with, it's in some sense very exciting, and in another sense also very, very, I think, humbling. I think we really are in this moment in time where we can do something really fundamental to advance the state of human knowledge, the state of human experiences for almost everyone on the planet.
Yeah.
Right, in terms of health, in terms of education, in terms of opportunities, etc. It almost becomes that it's our responsibility at this point in time to be able to use all this richness we have in data and computing.